members of ACCE, Managing Committee of Kakinada Center, student participants, faculty of engineering colleges, co-engineer friends, good morning. Welcome to today's webinar. I welcome to our center chairman, Engineer Badan Sundara garu. Welcome you, sir. I welcome today's speaker, Professor Suriya Prakash, IIT Hyderabad. Welcome, sir.
Thank you, sir. Thank you. Good morning, everyone.
Yes, sir. Kakinada Center, congratulate and welcome new members of ACCI enrolled recently. Balaji Chakravarti, R&D Department, Sarojini, Head of the Department, Prakash Engineering College, and our member Suriya. Aditya Engineering College Campus 2 given us the Education Life membership and enrolled recently. Earlier, Campus 1 is Education Life member. Now enrolled the Campus 2 also as Education Life member. Congratulations and welcome to new members to Kakinada Center ACCA. Coming to today's webinar on UPHC, High Ultra Performance Concrete, which has compressive and tensile properties multiple times more than the traditional concrete. The properties of this concrete are similar as hard rock. These concretes are helpful in constructions of structures exposed to continuous water logging areas like dams, structures which has continuous exposure to chloride penetrations like marine structures exposing low maintenance and prone to high abrasions like airport runways, parking areas, railway structures, industrial floors, lawns and bridges, concrete facades with slim sections. Expecting this webinar will help the participants get more aware of UPHC with Professor Suriya Prakash lecture about and developments and recent product provisions. Without late, I request Engineer Badan Sundara garu to share his views about this webinar and introduce our today's speaker. Sir, your voice is not coming, sir. Please give us 1 minute.
Good morning to all. Today, it's a great pleasure for me to introduce a great personality, Dr. Suriya Prakash. Dr. Suriya Prakash is a professor in Civil Engineering Department of IIT Hyderabad. He is a recipient of prestigious Ramanujan Fellowship from Government of India. Before joining IIT Hyderabad, he worked as a structural engineer, design engineer at Structural Group Incorporated, Baltimore, USA. He received his PhD from Missouri University of Science and Technology, USA in 2009. He obtained his MS degree in structural engineering from IIT Madras in 2005. His research interests include use of advanced composite materials for civil infrastructure, precast systems for affordable housing, and repair and rehabilitation of structures. He has more than 16 years of research and teaching experience and guided 6 PhDs and published more than 80 research papers in internationally reputed journals and presented more than 75 papers in national and international conferences. He is also serving as the associate editor for ACE Journal of Bridge Engineering and a member of ACI, ACE, ICI, IABE, and ASTR. He is also an executive member of Indian Institution of Bridge Engineers. He is also serving in the editorial board of ACE Journal of Composites for Construction and in various code committees of BIS and IRC. We are very happy, sir, to have you here for this
Yes, sir.
visible, sir.
Yeah, I'm going to put it in slideshow. Yeah. First and foremost, I think thank you for all your interest. On joining on a Sunday morning. So really appreciate it. So let me just. It's visible, right?
Yes, sir. Yes, sir. There's a small information, sir.
Yeah.
ACCE Kakinada conducting every month, one Sunday, this every webinar, sir. One webinar for every month, Sunday by 11 a.m., sir.
Okay. Oh, very
It's
nice.
our
Very
continuous
nice.
activity from past 3 years without break, sir.
Oh, very good.
Yes,
Oh,
sir. Yes.
without, yeah. Anyway, I mean, I'm very, very happy to see that ACC Kakinada Center is conducting very regularly these kind of events. I'm really happy to note that. I've also given in other centers also ACC Center. I'm always happy to share whatever the knowledge that we have accrued. So very happy to be there. First of all, thank you to all the office bearers of ACC Center for doing this fantastic job. I also see that participants are joined from throughout the part of India, which is very, very happy to see that. That means that ACC activities are very well received across the different communities. So really appreciated. So today I want to talk about ultra high performance concrete. Let me just put some pointers here. Yeah. So the use of ultra high performance concrete in structural applications. Okay. And we will talk about it's a relatively a new technology, at least from Indian perspective. And we will look at what are the opportunities and the challenges that are associated with that. Okay. Right. So is it? Yeah. So this would be my outline of my presentation. So first I will introduce what is UHPC because concrete has evolved over a long period of time. More than, Romans have been using concrete, Roman concrete for more than 2000 years. And then modern concrete is in use for almost 150 years after the invention of cement by Joseph Aspidin, and it has evolved over a period of time. Okay, so we will talk about what is ultra high performance concrete, what is the need for that. Then I will briefly give what are the various structural applications of ultra high performance concrete. Okay, so here this is a very special concrete, just like we deal with steel, concrete, wood. So it is a new type of structural material itself. You cannot really consider this as a one type of concrete. You have to compare it or treat it like a new class of material. So that is very important. Okay, so I'll talk about what are the various applications that we have. And then there are challenges. Okay, whenever any new material, new technology comes, it solves a lot of problems, but also it brings some challenges when you are implementing it in the field. So I will briefly talk about what are the challenges that you have when you adopt this new technology or new material. And then we have been extensively doing research on this ultra high performance concrete, fiber reinforced polymer composites. For last 11 years, we have developed state of the art facility. In fact, I would say in comparison to even world class universities, we have really good facilities that we have developed in the last 12 years at IIT Hyderabad. We have done a lot of work. I will briefly talk about what are the various things that we have done. And then finally, I will conclude my presentation with some summary and remarks. Okay. So you can interrupt me if you have any questions or comments, definitely we can take it up. Okay, so let me get into the first part of the presentation, which is what is UHPC? As the name stands for, UHPC stands for ultra high performance concrete. So please keep this in mind. We know high performance concrete, so we are adding one more word, ultra. So what does it really mean? Okay, so something excessive performance requirement than the normal high performance concrete that are already available. Okay, so what all those things? So if you look at it, we want three important properties in a concrete. One is, okay, SCC is, everybody knows, self-consolidating concrete. Sometimes people also call that as a micro concrete. When you have a heavy reinforcement and vibration is a process where you remove the voids. If you don't remove the voids properly, then air voids which are there in the system, it will create issues and it will create strength issues. Strength will be less. So that is the reason SCC was invented in Japan. Now throughout the world, in India also, we have been using excessively SCC, self-consolidating concrete, and it doesn't require any external vibration and it can flow on its own. And it can, we can use this material as this concrete for concreting structures with heavy reinforcement. Now, next thing is we know that concrete is very strong in compression, but very poor in tension. Okay, that is the reason we put reinforcement, lot of reinforcement, and steel is considered as a very good reinforcement that has very good tension strength as well as compressive strength. And so, how to tackle tensile strength, low tensile strength of concrete is one way is to put these discrete fibers. Okay, now in market there are so many types of fibers are available. We have steel fibers. Even in steel fibers, you have macro fibers and you have microfibers. There is a company called Beckett that is selling even in the steel macro fibers. You have 3D, 4D, 5D, depending upon how many end hook lengths are there. Okay, so fiber reinforced concrete helps in improving the performance of concrete in tension. Okay, so weak link in concrete is tension. So fiber reinforced concrete helps to improve the performance. Again, normal concrete flow is a problem. So self-consolidating helps to reduce the problem. Then durability in concrete is an issue. If you do concreting well, 100, 150, 200-year-old structure also we can do. But most of the time we don't do concreting well. So we end up with a lot of durability issues, mostly related to corrosion of steel. Okay. So again, high performance concrete was invented around 1980s or so, and basically to address the durability issues. So ultra high performance concrete is a concrete that combines advantages of self-consolidating concrete, advantages of fiber reinforced concrete, and advantages of high performance concrete. So that is the reason this UHPC can flow on its own. So it is like, it has a characteristic of self-consolidating concrete. It has a lot of fibers. It can tackle the tensile strength or low tensile strength of regular concrete. And it is very dense. So durability is also much better. So UHPC is a new type of concrete that combines all the, or addresses all the shortcomings of normal concrete. Okay, so that is a big advantage. In addition to that, we can also have a very good improvement in mechanical properties. Now let us look at this. I'm taking M50 concrete. Okay, so if you test a concrete cylinder in the lab and you get this kind of a stress strain curve, okay, that is what we use it to design structural elements. Because first to design, I need to know how the material is behaving in compression, tension, and so on, right? So this is a material, the black color is the one with UHPC that we have developed. In fact, anybody can develop. It's not a big thing, but you have to do a lot of trials and then you have to come up with a proper procedure to develop that mixed design. So what I am trying to tell here is, this concrete is having 50 megapascal, but this concrete can be designed to have 150, 200, 250, 300 also. So you see here, you get a tremendous increase in your compressive strength. Okay. So what happens because of that, I can reduce the size of the structural mass. That is a major advantage. In addition to that, you can also see that the stress strain characteristics are going to be different than your normal concrete. Okay. And the elastic modulus, which we call that as the stiffness of the material, is also going to be higher. And we know that EC is 5,000 square root of FCK as per your IS 456. Higher the compressive strength, higher will be your elastic modulus. So the moment I increase the compressive strength, all other parameters also increases. Tensile strength increases, shear strength increases, and so on. Right? So this is the advantage. Now this is very, very important. This is in flexure. So I take a small concrete prism and then I subject it to 4-point load. Okay. If that is the case, if I plot this load versus deflection curve, here again I have two curves. One is the red color one, another one is the black color. The black is the UHPC and red color is the M50. So you see here M50 at even a load of about 3.5 or so, it is cracking and it is failing suddenly. But if you look at UHPC, just as a typical example, this also I can increase it. This is in load, not in megapascal. So 3.5 has become almost 12. So it can take very high flexural loads, okay, very high amounts of flexural load. And also when it is failing, you can see that suddenly the capacity is dropping in this M50. But here the capacity is dropping very, very slowly, very gradually it is decreasing. So that means this material can sustain high strength in flexure, bending. Also, when it is right after cracking, it will not fail. It will give away its capacity very slowly. That's what we want as a structural element. You know, soon after it develops crack, we don't want failure. It should give sufficient warning before we can, look at some intervening techniques. Okay, so this is a big advantage. And the tensile ductility is greater than 3%. So what is the meaning of tensile ductility? When I test the same material in tension and concrete, you know that it is very poor in tension. And usually tensile strength is about 10% of the compressive strength. In fact, it varies from 5 to 10%, depending upon what concrete that you're looking at. But this ductility is the ability of the material to resist the load even after cracking or yielding. For concrete, it is cracking. So it, even after cracking, it can go and sustain the load for 3% of strain. Okay, that's a very high capacity for concrete. But usually concrete is going to fail at a strain of about 0.0001. Okay, if you multiply in percentage, it is going to be 0.001. So you can see here it is increasing multiple times. Then because I'm having higher compressive strength, higher tensile strength. Now if I'm comparing a bridge girder like a box section that we have seen here, if I do a conventional concrete, these are the dimensions. If I do UHPC, these are the dimensions. People have studied that. Okay, that's the reason now a lot of bridges are being built in India with UHPC. In fact, Government of India is also pushing this new material to be adopted. You can see the area of concrete. Area reduces by about 50% or so. The overall depth reduces. So there is a significant weight reduction. So the moment I reduce the self weight, when you go for longer and longer span, if I am able to reduce the self weight, I mean, my demand will come down again. So it's, you see, concrete is a major problem is we put a lot of material, and the self weight itself, the dead load weight itself is quite heavy. That is one of the things that problem with concrete construction compared to steel. Steel is very attractive because it's lightweight. Okay, so by using this kind of material, we can get into the realm of like a steel. You can make very light sections. Okay, that is a big advantage. And this is the example for a bridge superstructural element like box girder segment. If I'm using HPC bridge and normal bridge, you can see here for a normal concrete, if I'm using M50, I need an area, cross-section area of about 4.15 meters square. And here, 2.15 meters square. So roughly 50% it has reduced, right? Similarly, if you look at the amount of steel, pre-stressed tendon and reinforcement, you see roughly you get about 30,000 mm square of steel, okay? But here, you end up, for a normal bridge, you end up having almost 50,000. So you can see here there is a tremendous reduction in amount of steel also. So I use less material and I also use less steel. So that is a big advantage. So and most importantly, I think most of you must have seen Hyderabad Metro, right? And if you look at it in the city area, usually these bridge piers are spaced at about 25 to 30 meters, right? And metro, you know that it runs for about, we have now multiple phases are going on, right? So metro length, each phase can be 40 kilometers. So, and in each 40 kilometer, let's say if you're having every span of 30 meters, roughly, you look at the number of,
Sir, excuse me, sir, for small observation.
yeah,
Sir,
yeah.
there is gray box in your screen, sir. So it is some
This,
obstruction. Yeah.
is
Thank
it
you,
okay
sir.
now?
Right.
Yeah,
Sir.
yeah. Okay, so if you look at the Hyderabad metro, your number of the bridge piers that is required is every 30 meter, you put one bridge pier and then you put superstructure limit. So you end up putting lot of material. And also imagine, you are digging up for foundation. So if somehow if I can reduce the number of columns span and make the span from 30 meter to 60 meter, then you see you are definitely cutting down the number of piers required and number of foundations required, and then it is going to lead to faster construction, and you have a longer clear spacing so people can move across from one side to another side very easily. These are all big advantages. So same for this is a superstructure. Instead of having this the high performance concrete, when I'm using, I need to put a spacing of 2.5 meter here. Okay. And the same thing now here with this, I can go for 3.3 meters. So even the number of girders that are required, in this case, if you see 5 meters are required and the depth is also high here. And here I need only 4 girders. So for the same carriageway width. So I end up with number of structural elements, less number of structural elements. Okay. So that's what we talked about as in the case of example of your Hyderabad metro also, right? Now, another important thing is because we are going to use very fine material, okay, when cement reacts with water and all the aggregates, you form hydration products or calcium silicate hydrates. That is what it is giving strength to the concrete, right? Now, because I'm using very fine material, and in a regular concrete, the weak link is always, we call that as an interfacial transition zone. That is the interface between the aggregate and the cement paste is the weak link. Now, because I'm using very fine material in this UHPC, this fine material can go into the aggregate and it can form a very homogeneous surface on the interface. So you get a very dense hydration product and you end up with dense microstructure, and even porosity is going to be less and it is going to be discontinuous. Again, durability is related to the porosity and the interconnectivity of the porosity. That means if the pores are interconnected, then the water can flow from one side to another side, or water or oxygen or chloride, any other substance that is going to cause corrosion. If I'm able to make this pore structure discontinuous, then I make the concrete to be very, very durable. So this is the advantage. So it gives excellent protection against corrosion and excellent resistance to chloride penetration and low water absorption. These are all the advantages. And also it gives you excellent freeze and thaw resistance. The reason is freeze and thaw is not a big issue in India, but if you look at Northeast, sometimes the temperature can go less than 0 degrees centigrade, sub-0 degrees centigrade. There, if the water is getting inside, and then when water becomes ice, what happens is the volume increases. When the volume is increasing, then it is going to put pressure on the surrounding concrete and you're going to get a lot of cracking. Now, if water cannot enter itself, then, I don't need to worry too much about this freeze and thaw resistance. So these are advantages. Okay. Now, another example here is it has high durability and mechanical strength comparable to that of steel. So this is advantage with steel is you end up with a lightweight structure. You can go for a long span. And concrete has its own advantage. You can make it to any shape that you want, and it is highly durable. Fire resistance is a big advantage. So by making this material having high mechanical properties and addressing the shortcomings of the regular concrete, now also steel is prone to corrosion and it has fire resistance issue. Now what we are saying is we are taking advantages of steel and also we are retaining the advantages of the concrete. So in this way, it becomes a very fantastic technique for making structures. Now, if you see here the maximum span, okay, if I'm using a conventional concrete, I can go for 20 meters. If I'm using steel, I'm going up to 50 meter. I'm just saying one example. UHPC, even you can go for longer because now I can put pre-stress also. Okay. So these are the some of the advantages, and you can make this very complex structural shapes. That is another. That's why now, in fact, facade element are being made using UHPC. You can make a very thin, nice facade element, and that facade element is always in contact with water and external environment. So that is again a big advantage. Now, another important reason why we are going for high strength concrete is we want to go taller and taller from building sector, and also bridges we want to make it more longer and longer. Suspension bridges are, now people are talking about 1 kilometer, 1.5 kilometer suspension, 2 kilometer spans and all. Now, if you look at Chicago Water Tower, they used M100 concrete in 1990 it was constructed, and the height is more than 300 meters. In fact, Hyderabad also, if you look at it in India after Mumbai, Hyderabad is going to have a lot more skyscrapers, and a lot of projects are already started in the range of 250 to 300 meters. So especially in the financial district, Kokopet area, you must have heard, a lot of players are putting up very tall buildings. So again, Taipei 101 tower, if you look at it, M70 they used. And then if you look at Burj Khalifa, they used M90. And now Jeddah Tower, which is also called as Freedom Tower, again the work was stalled. Again they are restarted the work, and we are aspiring to go more than 1 kilometer. So as the height of the building increases, you want to put very stiff element. That is why the core element, the core we call it, core will always be made of concrete. Now with high performance concrete, again, I can go for with less area, I can still achieve what I want. So this is the reason why people are preferring to go for more and more high strength concrete. And that is it. Now let's see historical classifications. How do you? For normal concrete, you know that the strength is in the range of 25, 30, 40 megapascal, and your water cement ratios in the range of 0.4 to sometimes even 0.7 in the olden days. Because workability, at that time, chemical admixtures were not available. So the only way you can get workable concrete is by increasing the water to water cement ratio, water to binder ratio. Here we say that as a binder. Binder is all common terminology for cementitious material, right? So then high strength concrete was developed about 1985. Then people realized that, okay, the more water you put, the strength is coming down because you don't really need that much water for hydration, complete hydration. So they are looking at in the range of 0.28 to 0.4. And then self-consolidating concrete was developed in around mid 1990s. And that is again water cement ratios in the range of 0.3 to 0.4. Now, ductile is one of the first product in UHPC that was developed. They realized that you don't really not much water to binder ratio, even with 0.18 you can get, and they were able to develop strength in the range of even 300 megapascal. And then the ultra high strength concrete came into picture at about 2000 or so. It was developed in France, and then very significantly used in the Europe. Then US also started adopting, I would say, about 20 years ago. And now every state highway department in the US is adopting this in bridge construction. There are also several buildings that are being made with this UHPC. Now, ductile is another product which was developed in 2010. That is the range of 100 because this is for mostly for architectural concrete. And then we have again architectural ductile. One more product came in 2012. That also is slightly higher water cement ratio was there because these elements are very thin and so on. So what I'm trying to say here is if you want compressive strength high value, you need to somehow limit your water to binder ratio. Okay. So if you want in the strength in the range of 150 to 200, your water to binder ratio cannot go more than 0.2. Okay. So that is the point what I'm trying to do. Now, in terms of difference in concrete compositions, when you look at it, for normal concrete, the quality of raw material, if I'm plotting it in the y-axis, in the x-axis, if I'm plotting different concrete, quality of raw material for UHPC has to be very, very high. Okay. Even small change in the quality of the raw materials. See, this even when you want to make good concrete, obviously the quality of your ingredients should be good. But UHPC is a very special concrete. If you want to achieve whatever that we are aspiring for, then you have to select, and the quality of raw material has to be really good. Okay, which we will talk about. And binder, when you talk about, in normal concrete, we use only cement as a binder. In high performance concrete and ACCE, we use cement as well as supplementary cementitious materials as binder. In UHPC also, we do the same, cement and supplementary cementitious. And only in supplementary cementitious material, again, we have to limit the size of the material. And if you look at aggregate diameters, for normal concrete, usually about 20 mm, but sometimes we can also, with proper gradation, we can also go ahead and use low strength, high size aggregates also. But in UHPC, the size of the aggregate has to be limited to less than 2 mm. Okay, so then only I can get a better packing and get good mechanical patterns. So these are all some of the challenges that we need to be careful of. Okay, then fibers. Okay, this is another. I said fiber reinforced concrete is also one of the important things that we are going to add. So fibers here we don't add in normal concrete, but in UHPC we try to add in the range of about 160 to 180 kg per meter cube. Very large amount of fiber dosage also we add. Okay, so that is another thing. Now let's look at the flexural performance. Okay, because why is that I'm interested in flexure? Superstructural element always, if you go to a building or anywhere, we want a large column free space, right? We don't want to have columns right in the middle. Okay. So if I can get rid of the columns and make the span longer, then the utilization point of it becomes much more attractive, right? So that is governed by how the material is going to behave in bending or in flexion. Okay. So if I start plotting, let's say I cast a 200 mm by 200 mm beam and make it to a length of, let's say, 1.5 meter, and then I'm putting it in a universal testing machine, and then I'm testing it. You'll find the normal concrete will immediately crack, and it doesn't have any reinforcement. It'll fail like this. But if I'm having fiber reinforced self-consolidating concrete, fibers will increase your cracking load marginally. But even after cracking, it will not let it to fall very suddenly. So you'll have a gradual fall like this. This is, we call that as a strain softening behavior, because the load is not increasing after cracking. Okay? And in UHP FRC, again, you will have very high cracking load. And then after cracking, the material will not drop in its capacity, and it will drop in its capacity very slowly. So again, this is called, we call it as UHP FRC, ultra high performance fiber reinforced concrete. Now this drop, whether it is going to be flat or it is going to go very high, it all depends upon how much fiber that you are adding and what type of fiber that you are adding. So I can make it really high strain hardening or less strain softening also. Okay. Now, how do we get this kind of strain hardening behavior is, if you look at how these fibers, all these yellow colors are basically fibers. Okay. The moment it cracks, now these fibers will arrest the crack. Okay. Now, especially in the vicinity of the crack itself, when the matrix is cracking, first of all, it will delay the cracking. Okay. Even before the origination of the crack will be delayed to an extent. Then the matrix, the fiber will start debonding initially. And then the fiber, after a certain point of time, the length of the fiber is very short, then the fiber can pull out also. In fact, through pull out mechanism only, a lot of this energy absorption in the cracking process is achieved. Then finally, if the anchorage is very good, when the crack width is becoming more, the fiber can actually fracture. So this is what we call it as a fiber fracture or fiber failure. Fiber can also completely pull out also. It depends upon multiple factors. So these are all some of the challenges. This is the way the energy absorption mechanism due to fiber reinforced concrete arresting the crack happens. Okay. Right. So let's say, okay. So now in terms of raw materials, when you look at it, here in the x-axis, I have particle sizes. Let's see now what are the raw material that we are using. Now particle sizes are given in nanometer here. Nanometer means 10 to the power of -9, right? So you see here, for a conventional concrete, we are anywhere from 1000 to almost how many zeros are 7 zeros are 10 to the power of 7 nanometer. Okay, or in other words, up to 10 mm or 10 mm size, that 20 mm size that we use. Okay, this is in log scale. Okay, so this is about 1 mm to almost about 10 mm or 20 mm, we can say, right? But if you look at in your high performance concrete, the size of the particles ranges from 100 nanometer to almost about 10 millimeter. But in our nano engineered concrete is another special concrete where we use this graphene oxide, carbon nanotubes, all these nanoparticles we use, and we develop the mixed design. So their particle size can range from 0.01 nanometer to as high as 10 millimeter. Okay. So now in your UHPC, when you look at it here, if you look at your mixed composition or material composition, for a high strength concrete, your binder system or cement and supplementary cementitious system, it occupies about 33% of volume. Coarse aggregate is about 32%. Sand is about 17%. Water and superplaster is about 17%. But if you look at in UHPC, the binder obviously will increase. But you see that there is no coarse aggregate at all. Coarse aggregate becomes zero, and we use only fine aggregate, and that is about 38%. And then you also use, in fact, with this regime, particle size ranges from about 20 to 30 nanometer to almost up to 1 millimeter. This is the range our particle sizes are going to be in ultra high performance concrete. We are going to use a lot of silica fume, a lot of cementitious system, Portland cement, fly ash, and then we can also use GGBS and so on. Okay, so there is no coarse aggregate in UHPC. Now let's look at, if I take the small sample of a concrete and if I put it in a microscope, and then when I look at the size of the particle, and the bigger sizes are your coarse aggregate, and these small white color substances are your fine aggregate, and the small dark ones are your cement grain. Okay, you can see that the white spaces are all your voids in the system. Okay, and how closely that these particles I can pack them. Okay, and that is called as packing density. If I can put more materials within a particular cross section, then the packing density, if the white space is completely zero, then packing density will be 1. But it's very difficult to achieve because all these particles have this shape. So when you put the different particles together, you cannot always fill completely, right? For normal concrete, the packing density is about 0.6 to 0.6. But what we are trying to get in your UHPC is by limiting the size of the particle, what we are trying to do is we are trying to pack all small particles of different sizes so that I can reduce this white spaces inside the cross section. So that's why if you look at it, the white spaces are, see these white small particles are all particles. Okay, between them, whatever the space is there, that is your void. So by combining particles of different sizes, and also I'm limiting the maximum size. For example, you see, you don't see this gray color big particles. The maximum is the fine aggregate. These are all fine aggregates. And then you have silica fume, and then you have fly ash, and so on, right? And cementitious. So I can get as high as packing density of 0.85, 0.9 also. So what does it do? It helps in reducing porosity, and it improves microstructure, and it enhances the homogeneity of the concrete. So this is a microscopical image, okay? And what I told is this interfacial transition zone, ITZ. If you see that there is a small gap, but this is an aggregate, this is a cementitious system, okay? Between the cement paste and aggregate, you see a lot of voids. This gray color that what you see at the interface is the voids. But such kind of thing, you don't see it in UHPC. There is no voids at all at the interface. So that means that this is a weak link. The crack will originate here when you load the concrete. But if I'm removing this weak link, then you know that the mechanical performance of the concrete is going to be much better. Now, so we know that when you reduce the water to cement ratio, water to binder ratio, I can reduce the porosity and strength will go up. That's what we are trying to do in ultra high performance. But what is the cost that we pay? When I reduce the water, then workability also reduces. So then how to compensate for that reduced workability? I have to add high range water reducer or super plasticizers. And the super plasticizers also should be compatible with the type of cement and type of material that we are using. In that way, we can improve the workability. So this is the idea. Okay, now let's see what the mixed design is done. So a rational binder design or mixed design is based on the characteristics. Okay, I have to first target what is the optimum packing that I can achieve from the size of the material. and how reactive all these materials are. And also I should retain this self-compacting flow so that it can flow on its own. And also we need to talk about what are the aggregate class and quantity required based on the packing density that what I'm trying to achieve. Now, how do we evaluate the material properties of all the raw materials? Of course, we need to do mechanical testing, compression, tension, flexure, fracture. And also we need to, because this is a very highly durable concrete, it should satisfy some durability performance also. Chloride penetration, resistance to freezing and thawing and so on, right? Now, if you look at it, these are the raw material that we are going to use in your ultra high performance plant. Of course, cementitious content has to be high, and we need to use microsilica or silica fume. And silica fume, you see here, the size is almost limited to about only 20 micrometer. Okay, so it is anything less than 20 micrometer is silica. The red color, the orange color curve that what you see, and this is in the log scale. You see, the next is this is the 20 micrometer. You see, all the particles are between 15 to, in fact, 0 micrometer, right? So that is that fine material that we are using. And also we have GGBS, ground granulated blast furnace slag, and then we use cement. And cement, you can see that sizes as high as we get about again 20 micrometer, and it is less than that. And fly ash, you can get about 30 to 40 micrometer, and the size will be less than 30 to 40 micrometer. And river sand, you see here, this is the maximum. So that is about 2000 micrometer, which is about 2 millimeter. So this is the, you have to see the sand also, and to make sure that these gradations are all appropriate. Then we can combine this gradation to achieve final gradation for all the mixes. Okay, so that's what we do. Okay, so we select the binder materials, and then first we do the optimization of the paste. Okay, without any fine aggregate. So first we optimize the binder combinations for paste. That means how much should be cement, how much should be a GGBS, how much should be a silica fume, how much should be a fly ash. I make a paste out of it and then evaluate the mechanical properties and flow characteristics and packing densities. Then once we optimize that, then we go ahead and put sand gradation, and then we go ahead and add fiber volume. Then we find out preliminary water to binder ratio, and then what is the superplasticity that is required. And once we do that, now we are adding sand as well as fiber. Along with that, we need to evaluate the flow, and the flow should be greater than 220 or 250 mm. Then once we achieve the flow and we achieve these proper properties, then you evaluate the hardened properties. The hardened property for UHPC is at least it should have 120 megapascal. Now, if you're designing for a 200 megapascal, then obviously you again optimization you have to do. Then finally, if the strength is as per your requirement, and then if your flow is as per your requirement, then we can go ahead and finalize the mixed design. So this is the procedure that is given here, and this is what we do. Okay, so now how do we do? First, in our case, the sand and cementitious materials are combined, and we do dry mixing for about 3 minutes. And then what we do, we add a little bit of water and high range water reducer, and then mix it for another 2 minutes. And then once you add all these things, then you see this slowly it will form like a fluid. Then you add your little bit of polypropylene fiber also we add. These are microfibers for just for arresting the shrinkage, because in here in UHPC we use very high amount of cement content in the range of 800 kg per meter. So when you use such kind of cementitious content, shrinkage cracking can be an issue. So we add very little dosage of polypropylene fiber. Then again we mix it to 60 to 120 seconds, and then we add finally the steel fibers. Then again we mix it for about 2 minutes. Then you see that finally you get this kind of a mix, and then we check for a flow, and the flow has to be. This is the minimum mini slump flow test, and then once it's all meets the minimum requirement, then we go ahead and do the casting. Okay, now let's briefly talk about structural applications. Do you see here? Now we talked about how the mix design and how this UHPC material is actually realized. And you see this material is in use for last about 20 years or so. And if you see the Paris Museum, they've used this product ductile, which is a UHPC. Similarly, you look at this facade element. Very nice, intricate shapes can be made because it's a very highly flowable concrete. Without any reinforcement also, it will be able to take a lot of load. So that is the reason for facade element now people have been using this material and footbridge. Okay, and very long footbridge or bridges can be constructed. And this is a light rail station roof canopy. This is a roof canopy, very just like it looks like steel, but actually it is all concrete. Okay, and residential construction also we can make facade element and structural element using this. So these are all some of the applications. And in bridges, again, in precast, if you look at this, deck panels are made, and these joints are all done using UHPC. Why in connection we are using this? Because it is, if you see, a very highly flowable concrete, flow on its own, and your bond strength will be very high, and the embedment length for the reinforcement, even with very less embedment reinforcement, now I can develop the stresses. So they are used there. And bridge overlay application. What is the overlay? We put a small top layer on the bridge surface. Okay, this provides an impermeable layer because this UHPC is a very dense concrete. It will not let the water to get inside, and also can be used to strengthen the bridges. Okay. So I'll explain. And bridge girders are done. This is one pie girder, which was done in Iowa, one of the bridge in Iowa. Iowa is a state in the US, so this was done. And this is one of the bridge that it was recently done in Masalga of Latur, in the place called Latur in Maharashtra. And they use this U-shaped, trough-shaped UHPC girder. It was almost 111 meter. You can see the span. And you look at it, there is a old bridge you can see, and you see the number of spans. Every 20 meter, you have a big pier that is connected. Now you see, you got rid of so many piers just by increasing the span to 111 meters. So you see the amount of material that we have saved. Though we are using this material which is higher in cost, now I am reduced the foundation cost, I have reduced the number of structural elements, so you get a tremendous advantage, and also this material is highly durable. So these are the advantages that we get by using this UHPC. Okay, so another application is a tunnel lining, and usually this tunnel lining is also done, and thickness of the lining is usually tunnel diameter by 20. Now what we can do is people have done to resist the jacking force from the tunnel boring machine and bending moment in the lining, the grouting stage, people use UHPC. And now the UHPC lining is only tunnel diameter by 60. So with very less thickness, I can complete this lining of all the elements. So this is another application. And wind turbines. Okay. And wind turbines are usually done using fiber reinforced polymer material. But now when such kind of systems are also made using UHPC. So you end up with very thin shell element. I can go for a longer height, reduce weight, and very small cranes will be needed to lift and put it in place. So you can all made it using precast, and you can connect them together. And okay, so now let's see what are the challenges. Okay, so we need to use very low water to binder ratio to attain strength more than 150 megapascal, and we need to be self-compacting for bridge deck connections or other things. So when you want it to be self-compacting, you need to put lot of admixtures, and setting time is going to increase. So mix will not set. Then what you do? We end up putting, to increase the setting time, what we do? We add accelerator. Usually calcium chloride or calcium nitrate is added as an accelerator. Then accelerator, again, what it will do? It will reduce the flow, right? So it's a cyclical process. So you have to do a lot of trials before we get the correct thing. And cost is also, when you put large admixtures, again, cost of the concrete is going to go up. And we also need to use several types of fine powders. Okay, we need extremely fine powder to ensure particle packing and reactivity. Now, what are the different types of fine powders? Fly ash, GGBS, microsilica, all of them have to be readily available. And for constructing a bridge or something, the material should be adopted locally. But then when you are using locally available materials, the material properties will change depending upon where I am getting the material from, right? Fly ash characteristics. In fact, fly ash is being very readily used in construction. But if you look at from which type, what type of coal that is used in the thermal power plant, the fly ash also quality will change tremendously. So that is again a problem. And even for the same proportion, if chemical composition is different, then the performance will be different. So scarcity of again supplement is needed. Now, how long we are going to use this thermal power plant and get fly ash from there is not known, because now people are developing alternate power sources also. But currently still thermal power plant is a major power generation source, but how long that will continue, we don't know. So scarcity of SCM is also one of the things. And we need to have a very small aggregate size and higher binder content. And so because of that, cost will go up. And the moment you reduce your aggregate size and the quantity, creep and shrinkage issues also will be becoming higher. So these are all some of the challenges. Then again, fibers. When you orient the fibers, when you do a regular casting in a big level, you cannot really guarantee what will be the orientation of the fiber. If your fiber is perpendicular to the crack, let's say this is a beam that we are testing and you put a notch. If fibers are perpendicular to this notch, then it will arrest the crack better. So that's why you see the flexural performance is much better for a 90-degree orientation. If your fiber is parallel to the crack, okay, parallel to the crack, then it will not do anything. Okay, so this is the notch. Notch is vertical direction. Fiber is also vertical direction. The crack will not be arrested by the fiber. So ensuring a proper orientation of the fiber is also a big challenge. So this is another one of the things. Now, what we can do is casting method for highly fluid mixes. This kind of a trough at 30-degree we can cast, and we can let the concrete to go from one side to another side. In this way, in a beam kind of thing, we can always make sure that majority of the fibers are oriented in the horizontal direction. That will help in arresting the crack. Okay, these are some of the challenges. Again, fiber orientation, this kind of a channel kind of system, this can be adopted in a precast environment. But in a regular cast in place construction, this kind of a mechanism is very difficult to achieve, right? So these are all some of the challenges for making sure that the fibers are in the direction where we want. These are some of the challenges. Now, casting, again, if you look at it, during casting, again, you can entrap the ash. Okay, though it is self-consolidating concrete, you can have trap there. And these kind of vibration, what we do, and then when you do vibration, these voids will come to the surface, and usually that is the reason the outside surface, top surface will always have less strength compared to that of the internal concrete. So reduction in strength and failure pattern is also going to change. Okay. Now what will happen is you need to the mixture sometimes when you are using a normal mixer. In fact, for UHPC to ensure proper performance, what we use is a twin shaft mixture, which is a specially designed mixture, and it's a high-speed mixture, high-speed shear mixture we call it. You cannot use a regular drum mixer or pan mixer. We can use it, but if you're using a regular pan mixer or drum mixer, then your mixing time will become more. Then what you can do is you can overload the mixing also, mixing engine. So mixer engine can be overloaded. Okay, so this is the limitation. And mixing torque required for UHPC will be very high. Okay, so for conventional concrete, you don't need that much. So current existing mixtures have to be modified slightly, or we need to do it in low dosages and cast it in multiple batches. These are the things. So why is a high speed torque is required? It is coming from your mixing kinetics. Okay, there are different processes that happens. One is a wetting and nucleation process. First, that water that what we are adding or the admixture that what we are adding, it will be absorbed into the granules, and then you have this process called consolidation and growth, and this will start only after all the granules become wet. Now we are using low water to binder ratio, so the water from the wet surface will be squeezed from the inside of the granule. So these are different processes that it does. Then finally you have homogenization. To get homogenization, I need large mix time. So if you're using a regular mixes, then the mixing time will increase like anything because we are using low water to binder ratio. And you have this process. First, everything has to be wetted and nucleation has to be done. Then consolidation and growth should happen. Then the homogenization takes at a very large mixture. So for large scale production, we need a high speed mixture, and addition of ice cubes reduces the mixing time, temperature, and increases the flow. And number of modifications in the precast site mixes are required before we can successfully producing UHPC precast elements. And UHPCs nowadays are traditionally done using precasting. Very few constructions are done using cast in place, where you get it in your RMC. You know, in fact, we have only right now two producers in India. One is based out in Pune, and then another one is Dura. There is a company called Dura, which is a Malaysian technology that they have set up a plant in Pune. And there is one in Mumbai, UHPC India. They are the two major players that supply this material. In fact, they supply it as a pre-packed mix. In fact, a couple of my students are also now putting up a company. They will be supplying this material. Anyway, so this is the implementation. There is going to be challenges. What are the implementations? In India, for anything to be implemented, we need to have codes, specifications. Right now, we don't have specifications. We are, though France, Swiss, US, and Canadian guidelines are there that we can adopt, but Indian guidelines are not there. In fact, I'm part of the BIS, Bureau of India Standard, and this committee that we are looking at developing guidelines. So, and lack of industry experience is there, and batching, mixing, and how to incorporate steel fibers. Again, these are all challenges. And high material cost is a major thing. And we end up putting a lot of steel fibers. And steel fibers, this is a very special fiber. They are called as micro steel fibers. Their diameter is about 0.18 mm and length is only about 13 mm. So I cannot reduce the steel fiber to 0.18 mm just like that. I have to change the alloy composition. So the cost of the steel fiber, what we are using, is about 210, 220 rupees per kg. So that is again a cost is an issue. And we need a lot of good quality supplementary cementitious material, and admixture quantity is also going to be. So now BAS and IRC subcommittees are formed to promote applications in India. We are coming up with guideline, and it is in draft stage. Hopefully in another 3-4 months, I think it will come. Now, these are the challenges. Now, let's briefly, I'll talk about what are the research work that we are doing. So, optimization of mix design that I talked about, that is also going to play a major role. This is the PhD work of one of my students. And you see here, first trial we did, and we used cement of 890. I'm just giving some numbers, microsilica, so on, all. But you see the strength you are getting only about 40 megapascal. And setting time is also more than 40 hours, okay, which is not good. And flow, though flow we are achieving. Then again, what did we do? We reduce that mixture. Then what you get your setting time is less than 24, but what happens is the flow is coming less. Okay, so then what happens? Okay, now 53.4 liters became 26.7. Then it became 40. Then I get strength I am not able to meet. So like that, we need to do several trials before we get what we want. Okay. So again, effect of fly ash. You see, finally we were able to get this mix at about 7 days. We were able to achieve about 110 megapascal, and with a cement content, less cement content of about 700 kg per meter. So like that, we have to do a lot of trials, and using your particle packing method is there. There is a approach called Andreessen model. If you know the particle size distribution of all the particles, then you can get the combined gradation. And with that, we can get an idea how good your mix design is. So this is like this we are done. Then another thing is evaluation of your material properties. Okay, so this is the UHPC that was tested in fracture. That means I put a small notch and then I keep pushing it, and I see how the crack is progressing. Okay, if the crack formation is delayed and if fibers are able to arrest the crack well, then it is a very good design. Okay, so this is what we call it as a fracture test. And you see load, this is CMOD. CMOD stands for crack mouth opening displacement. That means in this notch, at the tip of the notch, or at the mouth of this notch, we put a sensor and we try to see how much this crack mouth is open. Okay, and you see here, even after a significant crack, first of all, it took almost a very high load of 22.5 kilometer. And then even after that cracking, the crack propagation is slower and the strength is not dropping very suddenly. It is dropping very, very slowly. And this is for a 2% of micro steel fibers. I can also play with these fiber dosages and fiber types, and I can make it to go strain hardening also. If I put 3%, it will go like this, strain hardening. So that is also possible. So this is another test, pure tension test. Okay, when you do it in pure tension, how this material is being. You can see in pure tension, I get a strength of almost 8 megapascal. Okay, in pure tension, usually you get strength in the range of about 7 to 10% of your compressive strength. Okay? In pure tension, if you are getting say 8 megapascal, means it's really good. And flexural strength, in fact, we were getting about 23 to 24 megapascal. And in flexure, in tension, we were getting about 22 megapascal, which is very, very high strength. And that is the reason we are very confident that this particular technology will work really well. And this is the flexion test I told. So at about even you can see at about you see multiple cracks are formed. Not just one crack, you have now multiple cracks that are formed. Whenever your system is able to generate large number of small cracks, that means the performance is good. So you can see that 35 kilonewton means this was only about 150 by 150. So if you divide by this area, you will get the strength of about 22 megapascal. Okay, so that is the reason we said we are able to generate. Then what we did from our test, we collected all the data from all the existing literature, and then we came up with an expression for an elastic model. Just like in IS code, we have no 5,000 square root of FCK. Instead of that, we said, okay, existing equation when you use, elastic modulus can be calculated from 0.85 times 5,000 into square root of FCM, where FCM is your cylinder strength. Instead of cube strength, here we are talking about cylinder strength. But in UHPC, again, the difference between cylinder strength and compressive strength of cube is not much. It is cylinder strength is only about 0.95 times of the cube strength. Then using all this data, finally I need to get some stress strain curve model to be used in design. So we came up with this kind of a multilinear stress strain curve that can be used for your design. And this RI is your fiber reinforcing index parameter. If you give what type of length of the fiber and what type of volume fraction of the fiber, then I can get the stress strain curve equation. So like that, we came up with again stress strain curve for tension also, because in regular reinforced concrete design, the major advantage with this thing is anything that is below the neutral axis in flexure, we say that concrete is not going to contribute in tension. But this material is going to give very high tensile strength, so we cannot ignore that. That is the biggest advantage with this material. So I need to have what kind of stress strain curve of this material is in tension. So again, we did a lot of work, and then we collected the data from various research papers, and we came up with this simple multilinear model. If you give me the compressive strength, this and fiber details, then you can get this stress strain curve that can be used for calculations. Then throughout the world, again, we saw that the behavior of bridge applications we are using, but this system, how is it behaving in shear? Because when it fails in shear, it is going to be a very brittle mode of failure. So how the system is behaving in shear, we tested several bridge girders like this, and then we evaluated the performance. So this is one of the tests like this. We have tested in very heavy shear, and you will find that even after first cracking of about 550 kilonewton, the system was able to resist a lot of load. And you see here the crack is forming here because it was tested in 3.1. And this, wherever this red color, you can see the crack. That's where the crack is forming. And so we looked at, if I change these fibers, what will happen? And if I change the amount of pre-stress, what will happen? All those things that we studied. And we found that the amount of pre-stress helps in increasing the cracking load and helps in increasing the peak load as expected. And similarly, if I change the fiber dosage also, it is helping me. For example, if you look at P35 and P70, if you look at it for same fiber dosage, now increasing the pre-stress helps in improving the performance. So that's what we said. And this is for 1% fiber dosage. P0 means no pre-stress. If you put 35% of your pre-stress, you get a performance improvement. 70% means further improvement. So the cracking load is found to increase with the amount of pre-stressing. Ultimate load also increased. So these are different things that we have understood from our research. Now all these things will go as a guideline for your what we are developing for IRC and ACCE and the design guidelines that what data. Now this also material can be used for strengthening of the beam. So we evaluated, okay, for an existing beam, if I put this kind of an overlay means what we do is we chip the concrete at the top and we put a small layer of about here I think we used about 50 mm or so. This is again one of the PhD students' work, and we tested this strengthening. You see here, this is a beam that was without any of this overlay, and UO stands for UHPC overlay. The moment I put overlay, you can see that strength increased from 100 kilonewton to 160 kilonewton. Stiffness also increased, and also the ductility at failure was not very high. Okay, And we looked at, okay, for bridges, especially strengthening is an important area. When I combine this UHPC overlay and FRP laminate at the bottom, how the system is going to behave. So that is also, again, we looked at it and we tested several beams, control beams only with overlay, and then we looked at overlay plus FRP. Like that, we played with the different combinations. We found that, and these are some of the details. Okay? In fact, I can share the PDF copy of this. You can use it. And we found that this UHPC overlay, for example, these are the different techniques, load versus deformation curve. And you can see that the hybrid system with the fabric and overlay, the strength became 100 to almost 220 weeks. That means for an existing girder, if I can apply this UHPC overlay plus this FRP strengthening, I can double the capacity. I mean, because you have to do the calculations and the stiffness also can be. So it's a very good strengthening technique also for existing systems. So that is what we have said. Again, we looked at for buildings. Okay, if I want to use this as a column, okay, and this is a costly material. So I put a new normal concrete, and then if I put additional material as an UHPC, this is going to protect this NSC normal concrete, and we can lead to composite column. So it is lead to reduced dead load, high strength to weight ratio, and it is going to increase the ductility, and it is also going to protect against the harsh environment. So we did. Why did we do that? And also this can be used as a strengthening also. When you do normal concrete, again, the problem is every some point of time, there will be degradation in performance. So then again, you do some repair, again after some time, degradation. Okay, this is for normal concrete. So this is the service time. But with UHPC, what I can do is with this composite column, first time maybe the cost may be slightly high, but if you see that the degradation performance will be very, very slow or very low. So these are the advantages that we can get. And we also looked at how the composite column behaves with a normal concrete. So this is a normal concrete column of 300 by 300. You see it is taking only 4,000 kilonewton at a particular displacement. The moment I make it as a composite column, I can increase the capacity from 4,000 to almost 9,000 kilonewton. So now you can see I can either reduce the number of columns or I can go for a longer span of the beam, so that with same cross section I can support more load. And columns always subjected to not only axial compression, you'll have axial compression and bending also. Again, we did a lot of testing for columns under different combinations of this compression bending. And this is your famous interaction diagram. I think several of you must have used this SP16 when you're designing. And these kind of design charts can be developed. Now you see here, with this composite column, I'm getting very good performance improvement in compression as well as in bending and all combinations. So with same cross section, now I can support more bending as well as axial compression. So these are all some of the advantages. Then we also looked at surface preparation, how the surface preparation is going to behave. Because when I'm putting a new UHPC over an existing column, then the bonding between the new concrete and the old concrete has to be good, right? So that is, again, we did a lot of testing. And we also, for Indian Army, we looked at if I use this material and putting it under high strain, it means, let's say your bomb is blasting, or when, in army structures, we want to store our missiles and all, right? So at that time, to protect our armory from enemy attack, our system should, be very rigid, right? And it should not damage. So we looked at all these things, okay? For air-based structures, you can use this UHPC. And these are underground nuclear storage facilities, nuclear power plant, your containment structures has to be very, very good, right? So for all these things, this material is going to behave very well. So how to test this material is good or not? This is one facility that we have created in IIT Hyderabad. This is called split Hopkinson pressure bar setup. And this can be used to test material. And this is a figure that we are showing. Normal concrete, fails at a very low strength. But you see, the same thing, if I test it at the same velocity, UHPC is able to give a strength of almost much higher than that of the normal concrete. And we applied a striker velocity of 10 meters per second, corresponding to a strain rate of 1 by 75. 75 is the strain rate. So you see here the UHPC performed much better than normal concrete. So like that, we can see. So in summary, what I can say is UHPC has a tremendous applications in bridges as well as in buildings, but more so in bridges. And UHPCs are more sustainable and durable in harsh environments, and it is a very viable solution for retrofitting existing structures. And again, UHPC composite column has a great potential in buildings, and proper mix design care should be taken for large scale protection. So this is again, this is a new material, new technology. So your mix design has to be done very, very carefully. And especially again, lab scale, everything will work well. But when you're implementing it in large scale construction, you have to do a lot of trials and ensure that quality control is properly maintained. Okay. So with that, I think I'd like to thank, these are all some of my students, their PhD work. And we also took help from various agencies. And I would like to thank them also. And if you have any questions or comments, definitely I will be happy to present. Okay. So with that, I think I will stop here. If you have any questions, definitely I'll be happy to answer.
Thank you very much, sir. Excellent presentation, sir.
Yeah.
Sir, I have a small doubt, sir.
Yeah.
From deflection point of view,
Yeah.
when compared with this regular RCC elements, is there any code for making the minimum thickness criteria, sir?
Okay. I mean, those are the things. There are French guidelines and Swiss guidelines are available.
Yeah.
Now, American guideline is also coming. But
Yeah.
once you know the material properties, we can do our own calculations. So you don't really need to follow. I'm saying without code also we can design. For example, let's say we know that deflections have to be less than certain values. Let's say 20 mm for short term and long term, so on, so like that. So we can do that. But what we need to know is what kind of elastic modulus I need to use. Okay. So elastic modulus, if I know the compressive strength of this concrete from what we have done our research, again we can use them. So the codes are being developed in India also. We are taking provisions from all the existing codes and we are coming up with the provisions. Once that is there, we can readily use it. Or until that point of time, we can use French guidelines. Usually the French guidelines are now, people are using it to design.
Yes. Another question, sir. From cost point of view, when compared with M50 concrete, what will be its cost in percentage wise?
Yes. So that's why I'm saying cost is definitely high for 1 meter cube of concrete. What we have developed in IIT Hyderabad, it gives you strength of about 150 to 160 megapascal, and you can go higher also. It cost about 85,000 per meter cube, including all the, that's what our students are selling, and it costs about 85,000 rupees per meter cube of concrete.
Cubic meter. Yes.
Yeah, cubic meter.
And
M50 probably, I'm not sure what would be the cost. If it's SCC again, micro concrete and readily available, I would say probably around 30,000 or so it will be there.
Yes,
so you are looking at this would be about twice costly, 2.5 times costlier than your M50. And but you look at the other savings. You reduce the number of structural elements, you reduce the foundations required, and overall material what you're going to use is going to be less. So if you look at all this thing, and also you're going to get a very maintenance-free structure. Okay, so considering that, if you look at it, it is going to be a very, very
almost we are getting 3 times higher strength, and the cost is also in the same proportion. So ultimately the sections will become slim, and spans can be increased. Thereby, indirect saving will be there.
Absolutely, because
we heard from one of the expert that cost of this steel per kg of steel is 90 rupees, and cost of this UHPC is around 40 to 50 rupees. In savings, there is a saving in material, like using of less steel, there will be in economy. I heard that, sir.
Correct. Yeah, that is a thing. So you end up putting less steel, and also with this material, always we apply pre-stressing also. When you do pre-stressing, then it becomes much more attractive.
Yes, sir. And one more question, sir. What is the care to be taken for curing?
Curing, okay, the curing process is normal curing only. But only thing is we are using this high cementitious content. No, the shrinkage strains will be on the higher side. But again, you have fibers, so that will help. We are adopting normal curing. Whatever that we do for normal concreting is only is we are also doing. But while during mixing process, we have to reduce the temperature. So what we need to add is a chilled water. You know, in your water when you are adding, either you put a lot of ice or put a very chilled water during manufacture. That helps in uh, reducing the shrinkage cracks like anything.
Yes, sir. Thank you. Thank you, sir.
Thank you. Thank
Good
Yes, sir.
afternoon, sir.
you. Good afternoon.
Sir, this is Dr. Panisula from SRM.
Hello,
Uh,
sir. Hello, how are you?
Yeah, fine, sir. Fine, sir.
Nice to
Fine,
see
sir.
you. Nice to hear from you. Yeah, please tell me.
Yes, sir. I have a small clarification regarding as you are adding the CFRP, what is about the delamination, sir?
Delamination, we have to be careful. And in our testing, actually, we didn't see any delamination. Let me just go back. Yeah, that, there is a debonding strain that we have to be careful. Okay, so here you can see this test, what we have done. This, we failed just slightly at the interval, but that happened. That is also minor, that horizontal crack we developed. But finally, things are okay. I don't know whether I have this failure modes of the other specimens. Because of the time limitation, I did not include that. But in our cases, delamination was not observed. But again, you have to be careful. In ACCE, when you are using, there is a provision for calculating your debonding strain that we need to make sure that it is not exceeded.
Okay, sir. Thank you, sir. Thank you, sir.
Thank you. Thank you. Thank you.
Yes, sir. I have a few questions, sir.
Yeah,
In
please.
this concrete, you mentioned that cement, microsilica, GGBS, fly ash, and sand is the ingredients. Here, the sand is only the coarse aggregate, sir. You mentioned that coarse aggregate percentage is 32%.
Yeah. Yeah, that's a typical, I just gave an example. Okay. Again, if I'm developing a 200 megapascal or 250 megapascal, the proportions will slightly change. But in general, there is no coarse aggregate. And the aggregate sizes are usually limited to 2 mm. If I go for a large size aggregate, no, then I cannot get that packing. So that is the reason we are limiting the maximum size. So the whole idea is in the particular volume, I want to pack as much as possible the material. That is possible only if I am limiting the size of the aggregate. That is the reason we are limiting it to 2 mm. But now people are also using some 5 mm, 6 mm aggregate also. But there you have to really tweak and make sure that you are achieving the packing what you want. But typically in UHPC, the size of the aggregates is less than 2 mm.
Okay, sir. One more question, sir. Under this UHPC category, what is the minimum grade of concrete? What is the minimum
Usually, as
starting
per
grade?
the as per the codes that are currently available, different codes give you different values, but the minimum is 120 megapascal. As per the French guidelines, if a concrete strength is exceeding 120 megapascal, and also it should satisfy the flowability and it should also satisfy durability requirement. Then only you can call this as an ultra high performance concrete. Not only the strength, we should also make sure that it is flowable and also it is having minimum tensile strength of, I think 6 megapascal is the minimum tensile strength. Okay. And the tensile strength minimum also we need to achieve, and also durability also we need to achieve. Then only we can call this concrete as an ultra high performance concrete.
Okay, sir. One more question, sir. You mentioned that the orientation of the fibers will affect some strength of the.
Yeah.
How to control this orientation, sir, during casting
I
only,
said,
or
yeah, in pre-casting, when you do, especially for, we use this for columns, it's even random orientation of fibers is not a major parameter per se, because majority columns are compression members. But in bending, what we do is you have to keep and make it flow using like a trough, which is at an angle of 30 degree or so. Then you kind of get that more or less horizontal orientation of the fiber. When the fibers are horizontal, no, usually your flexural cracks will be 90 degrees. So when your fibers are horizontal, then you get the maximum efficiency. But then the randomness you cannot avoid. But if you can get majority of the fiber orientation to be in the direction that is going to arrest this tension crack, then you get what you want. But in your casting-based construction, it is very difficult to achieve. Then what we do is to calculate how effective the fiber is. We use this factor called fiber orientation factor. That people.
Sir, please unmute, sir. Please unmute.
Yeah. So what I'm
Yes.
saying is fiber orientation factor has been derived and it is given in the French and German guidelines. That can be used to see what are the fiber orientation.
During vibration, the orientation of fibers may change, sir.
No, these are very thin fibers. That's why its size is limited to 0.18 diameter and length is only 13 mm. Okay, that's why we call this as micro steel fibers. And these are very nicely distributed. And during vibration, in fact, this material doesn't need any vibration, but some minimum vibration if you do. Also, even if you do good amount of vibration, the distribution of fibers will not change because they are distributed anyway in the mixing process throughout the compound.
Okay, sir. You mentioned that it's a low binder ratio and long mixing time. What will be the minimum mixing time, sir? Is there any guidelines?
Those are the things that we are now generating data from different guidelines. But here, what we use is a regular simple pan mixture in our application. Okay, and when we did that, we need to mix for about 25 to 30 minutes for a volume of about I would say 1 meter cube. You need to mix for about 25 to 30 minutes for each batch. But if you are using a twin shaft high speed mixture, then within 10-15 you can reduce by half the mixing time. So that is ideal. For the same volume, if you are using a high speed mixture, the mixing time will reduces by about roughly half. That's what our trials are telling.
What will be the density of this concrete, sir? As usual as this concrete.
Density is not going to change. Slightly it will increase because we are using 2% of your steel fiber. But rest of all the materials are nearly same as what we are using it in fly ash. It is nearly same to that of cement. Similarly, GGBS. So the density slightly increases but doesn't change much.
Okay. And you mentioned that it should be tested in a cylinder, not in regular cubes.
No, that is the American or this practice, but there is a correlation between cylinder and cube also. But here we test 100 mm by 100 mm cube, okay, because the size of the aggregate is very small and also the capacity is high. So, and if you test 100 mm by 100 mm cube, it is good enough. And cylinder strength is more accurate representation, but there is a correlation between cylinder and cube strength. And usually the cylinder strength is about 95% of cube strength for this material. For regular concrete, cylinder strength is about 80% of your cube strength. What we are using 150 by 150. If I have to convert it into cylinder strength, it is about 80%. But here the relationship is nearly same, because the size of the aggregate plays a major role in the difference in the strength. And here the size is very small. The maximum size itself is 2 mm. No? So there is no big change in your strength values between cylinder test or cube test. But cylinder test is about 95% of the cube strength. Cubes also can be used.
What are the dimensions of the cylinder, sir?
Cylinders, we are saying 100 mm by 200 mm cylinder, and cubes are 100 mm by 100 mm by 100 mm.
100 mm is diameter, sir.
100 mm is diameter, height is 200.
2 times.
Cylinder always should have a minimum length to diameter ratio of 2 when we test a cylinder.
Yes, sir. Could you please give an update on this BIS standard, sir, as you are the member of this BIS? Could you please give some updates, sir?
No, actually, this ICA, not BIS. BIS, we have been pushing them to form a committee. In fact, ICA, we are working with them, and also there is an committee from IRC, Indian Road Congress. Also, we are working on that. So those things will be released very quickly, and we are working on that.
Yes, sir. I'm going through this questionnaire from this chat box, sir.
Yeah.
HR Girish given a big appreciation to Kakinada Center. Hats off to Kakinada Center for such consistent programs every month. Thank you, sir. Thank you very much. And Kovar Ramchandra Reddy, Vice President of Rajmundry Center, mentioned that wonderful lecture.
Thank
He's
you.
appreciating this. Yes, sir. And HR Girish mentioned a question, sir. As crack develops in UHPC, fibers retard rate of cracking. This is defensive approach. Why not consider a further process of remediation such as adding bacteria, alkali piles to repair, refill the cracks, thereby further adding to durability factor.
Yeah, that is a lot of people are working on now, the self-healing and bacterial concrete that can heal on its own. And UHPC, I'm not sure that people have tried, but yeah, that is a good suggestion. But see, that's again, it is working very well in the lab scale. But when you implement it in a large application, at least I am not aware of what are the latest development in that field. But it's a good suggestion. It can be explored. But right now, yeah, I don't have much idea. But it should work when you add it and if it helps. But see, the problem is, and UHPC is always used in conjunction with pre-stressing. Always high strength concrete, you use it with pre-stressing. Okay, and in that process, the whole idea is, we want to design a crack-free element. Even if crack is forming, the crack width will be so minor, even your regular hydration product should be able to fill, further hydration product should fill. But again, this is also a good suggestion that may help also. But yeah, I am not sure what is the state of the art.
So there is question from Govind Rajan from Aditya Engineering College. Guidelines for design methods for high performance concrete.
Yeah.
He is asking
Guidelines,
about
guidelines, as you said, right now we are using French or German guidelines. French guidelines are very commonly used. But in India, I think it will take some time. Right now, we are coming up with this guideline and we are working on, I would say 70-80% is done. Then it will go through review process, and then by the time it comes out, we are looking at another 6 to 8 months. That is also guideline, not a code. Okay, so it will take time. It is work in progress. Yeah.
Yes, sir. Dr. PSN posted a very high potential for the UHPC, especially for retrofitting works, an area where the ever increasing gap can be filled to some extent with sharing of know-how to IITH. Excellent presentation. Thanks a lot to speaker and team ACCE Kakinada.
Yeah, thank you, sir. I think it's a very important area, retrofitting area. And I think, again, as you said correctly, UHPC can play a major role in that. And we are looking at multiple combinations, UHPC with FRP plus with, so it's a very good area. Yeah, thank you. Thank you very much.
Hope say student question, sir. One of the student asked a question, sir. What is the lifespan of UHPC for a structure?
Yeah. Lifespan, because the durability is enhanced significantly, I would say minimum, 100 years definitely easily we can achieve. But more than that, I don't know, studies are not there. How long it will last? See, even for a regular good concrete, if you do it properly, we have seen that. If you do proper concreting and use proper ingredient, proper curing, concrete structures can last even 200 years, 300 years, if you do it properly. Now with UHPC, again, we have eliminated the corrosion. So we have made it more micro dense. So obviously the life is expected to be much better. So I would say minimum 100 years easily we can achieve, but more, I don't have the information. Maybe, more studies should, at least I don't know what are the other people have studied. Minimum, I can tell you 100 years definitely we can achieve.
Sir, another from Engineer HR Girish, sir. Dr. Suriya Prakash, sir. Is it not preferable to carry out a detailed and holistic comparative costing approach considering sizing of elements, maintenance cost, retrofitting cost of conventional cost. Perhaps this may reveal UHPC construction to be more economical and sustainable.
Correct. No, that is true. For one particular case study, in fact, we need to do. I just gave you one example for a superstructure, but that is only from material cost. Okay, now you are reducing other elements and you're reducing your construction time. So many other parameters have to be included, and that comparative study, at least we have not done that. But for I think Dr. Satish Jain from UHPC India, I was listening to his presentation. They have done it for buildings, okay, and they were able to show almost 40 to 50% reduction in cost. Again, it also depends upon the volume. Okay, if you are having large volume, then you can optimize. So there are several factors that are involved in it. But at least at the outset, I can say it is definitely will work out to be economical when you have minimum volume that is there. For example, when you're looking at a bridge construction of 3 to 4 kilometers, then you produce the same elements, multiple times. So there, I'm not sure any such comparative study is there. I have to look into it. Definitely, I think we will consider this.
Unmentioned. Dr. N. Ram Prakash, one of the founder member of ACCE, I want to speak with you, sir. Yes. Welcome, sir. Sir, unmute, sir. Please unmute, sir. Dr. N. Ram Prakash.
Hello, Dr. Suriya.
Welcome, sir.
Wonderful presentation.
Thank you, sir.
Can
Thank
you hear
you.
me?
Yeah, I can hear you now.
Yeah, thank you. I have a few questions. One is, what's the effect of shear in these things? Has there been a study of the shear factors, building and shear? And second question is whether any work on torsion has been done, because torsion is also another factor.
Correct.
That is the second question. And the third one is, in the French codes, is there been a touch on, the orientation of the distinct fibers and the length of the fibers, the diameter and things like that? Is there anything in the latest of the codes, like the French code, as you said? Yeah, that's it.
So third question, let me answer probably in the reverse order. The French guideline gives you this fiber orientation factor that takes into account the diameter of the fiber and the length of the fiber and the aspect ratio of the fiber and all. And it gives you this orientation factor. Using that, we can calculate how much fibers will be effective in arresting the crack. And second question on torsion, usually, in torsion, of course, it is a significant concern, especially when you have an equilibrium torsion. I am not sure what is the current state of the art. I can tell you there is very limited information is available on how these elements will behave in torsion. So maybe I think people should look into it. But in flexure, there's a lot of information that is already available, and people have tested beams and girders of various sizes. And shear again, because usually we design these elements to fail in flexure before it fails in shear. So again, less amount of work is there. But when you have a post-tension girder with a huge point load that is coming, shear failure is an issue. That is the reason, in fact, we have taken up a work, extensive experimental work, and we are finding that fiber dosage plays a major role. And when you have a huge point load and DP action, then your behavior changes quite a bit. So we have done, and also there's a lot of work that is currently being undertaken for addressing the shear behavior. And the reason is, again, the cost of the steel fiber is a major thing in UHPC. If somehow we can optimize this fiber dosage by putting even regular steel stirrups, then you can ensure the performance. So that is the one work that we have been currently doing it. Throughout the world also, people are exploring that. But flexure, yes, quite a good number of studies are existing. Already we have a fairly good idea how the system behaves in flexure.
Thank you.
Thank you. Thank you, sir.
Yes, sir. Is there any query, sir? Engineer HR Girish? There is a raised hand in your box.
Sorry, sir. Sorry. I should have lowered it. Anyway, thank you. Excellent webinar, sir. Thanks.
Thank you,
Thanks,
sir. Thank you.
all of you and Dr. Suriya Prakash. Thank you, sir.
Thank you. Thank you, sir.
Ram Prakash, sir.
Yeah.
You are a role model to all of us, sir. At this age, your patient listening is very exemplary, sir. We are,
Thank you.
we are highly thankful to you, sir, for attending this webinar.
Yeah, thank you. But
You
I
are
would,
role model,
I would
sir.
like to thank Kakinada Center first, as
Sir.
Girish has put it, and also Dr. Suriya Prakash. It's a
Thank
very
you, sir.
extensive presentation, which is wonderful. Only thing I have only corollary to Dr. Suriya Prakash. Wherever it's implemented in India, it's better if you have an oversight on what is happening, because I don't want this technology to fail and people to say that technology has failed and things like that. It is a wonderful technology. The only thing is it can fail due to other mistakes other than of the product. So till it is established, I think so we have to have a oversight over all the places where it's being implemented. This is only a suggestion. Just thank you.
Sure. Thank you, sir. I think, yeah, we are pushing. That's why this guideline also quality control is a very, very big factor because, you know, in your design, if you're using high strength and if you're not able to achieve it in the field, then it's a big challenge. As you said, used also. That is, we have to be very, very careful. And precasting is one way to ensure that quality control is done properly. But then, you know, wide scale implementation will happen when you go for cast in place. So especially in building sector. And so we are working with various agencies. Definitely, I think point well taken, sir. Because lab scale, we can show it works well. But in field, if there is some one failure also, then it will push the technology backward. So your point is well taken. Yeah.
Thank you.
Dr. Ram Prakash is one of our founder member of ACCE, sir.
I see.
He's a very senior most consultant at Bangalore, and he came to Kakinada and given a lecture at that day, sir. Hats off you too, sir. Hats off
Thank
you, Dr. Ram Prakash, sir. And sir, one question, sir. Is the draft released by BAS, sir?
No, it is still not ready yet. So we are,
you mentioned that in 4 months, is
CA.
in about 6 months, I'm hopeful it'll come through. Yeah.
okay.
Because
Right,
see,
sir,
these
there is-
things go through several rounds of revision and all. So it may take some time.
Yes, sir. Another is from Dr. PSN, sir. In
Yeah.
the cross section of a flexural member, the compressive strength of the concrete is underutilized due to the cracked section approach. This UPHPC is a big game changer and hence must be economical considering the effects of reduction in self-weight due to slimmer sections and reduced maintenance cost due to crack control.
Yeah, definitely. Yeah, that's the whole idea. More importantly, you know, we are also using the tensile strength of the concrete. And when you use it with the pre-stressing, then it becomes very, very attractive. So that is the whole idea.
Any more questions, sir? Can we close? Now, vote of thanks by dear Durga Prasad.
Yes, sir. Thank you, sir. My special thanks to today's speaker, Professor Surya Prakash, IIT Hyderabad, for accepting our request and spending his valuable time on this Sunday to our members' knowledge sharing. My sincere thanks to ACCA team, ACCA head office team for their encouragement and support by providing this WebEx platform. Thanks to our managing committee of ACCA Kakinada Center, faculty of engineering colleges, co-engineer friends, participants from all around India. My special thanks to our member Sunit for his support in this webinar organization. Thank you all.
Okay. Thank you all. I think thank you for the opportunity. It was nice interacting with you all. Thank you.
Sir, we'll have other lectures from you, sir.
Sure,
about
sure.
this retrofitting.
Whatever is possible from my side, definitely I will.
Yes, sir.
Definitely.
One more request from our side, sir. We want to listen about this 3D printing technology. Sir.
I will see. The time was very limited. I'll speak
Yes.
with my colleague.
Yes,
Prof.
sir, yes, sir.
Subramaniam is there. I
Yes,
think
sir.
definitely I'll put a word to him because the time was limited. I could not push him. So
Yes, sir.
maybe definitely I'll ask him to request him to.
Sir, please support us for the next month lecture, sir. For every month, one Sunday we are conducting this webinar, sir.
Sure.
Any Sunday we are ready to hear
Sure.
that lecture, sir.
Sure.
Please support, sir. Thank you, sir.
Definitely. Definitely. Thank
Yes,
you,
sir.
sir.
Thank you.
Thank you.
Thank you.